And that pretty much does it for valence bond theory. Now the next idea is molecular orbital theory. And molecular orbital theory is different from valence bond theory in that valence bond theory is just talking about combining molecular orbitals, whereas valence bond theory is talking about combining all the electrons and all the atoms and everything together. Okay, so let's just talk about those contrasts. So valence bond theory combines orbitals only on the central atom. On a central atom. MO theory, molecular orbital theory, combines orbitals on all atoms. Not just a central atom. Okay? So, lucky for you all, we're not going to get into large, complicated atoms and molecules here. We're going to be sticking to row 2 of the periodic table, and we're just dealing with diatomic molecules. Okay, so 2 atoms, each molecule. Now, molecular orbital theory can deal with much, much larger things, but boy, does it get complicated real fast, and you'll see how quickly things can go awry. All right, so, but let's talk about our most basic example, our simplest example is dihydrogen. Okay, so the idea with molecular orbital theory is that I'm going to take and look at the orbitals that each of the hydrogen atoms has. Okay, so if I'm sort of drawing another thing that is looking at energy going up, I'm going to have 2 1s orbitals. There's one of them, and I'm going to combine it with another one. Right? And we can call this hydrogen A and hydrogen B. Right? Each of the hydrogens that are going to combine to make dihydrogen. Right? So each one of these is a 1s orbital. And that gives me 2 molecular orbitals. Right? One from each hydrogen. So what's going to happen here is that they're going to combine in 2 different ways. Okay, so if I have 2 molecular orbitals, I'm going to get 2 combinations. Okay, and so what happens with one set is that the 2 orbitals will combine into sort of a homogeneous little blob. Okay, and we refer to this one as a bonding orbital. All right, and we will, since we're dealing with 1s orbitals, we're going to call it sigma 1s. Right, because our bonding orbitals are sigma bonds. Right. The other possibility is that they push each other away. Right, so what we'll have is a node, and we'll have our things on the other sides, and they'll shove each other away instead of combining. Okay, and we refer to this one as an antibonding orbital. Okay, and we'll give this a sigma star 1s. Okay, so the star denotes antibonding. No star means bonding. Okay, and notice that the antibonding orbital is higher in energy, so it's less stable. Higher energy, less stable. Right? And the bonding orbital is lower energy, more stable. okay? So this is how molecular orbital theory differs from valence bond theory. Valence bond theory is talking about hybridizing and mixing orbitals and making new shapes, whereas molecular orbital theory very simply shows us what kinds of bonds can be made, okay, based on combining molecular orbitals. So the common notation, so the most common way for us to show this is with what we call a MO diagram. Okay, a molecular orbital diagram. Okay, and the way I'm going to do this is I'm going to take, on one side, I'm going to have my hydrogen A and show that it has a 1s orbital with a single electron in it. Okay, and then on the other side, on the far side, I've got my other hydrogen atom, my hydrogen B. And we'll say that it also has a 1s orbital with a single electron. Okay. Now between them, in the center, I'm going to show my sigma 1s and my sigma star 1s. Okay. So in here, I'm going to make these blue so that they're a little different. Slightly lower in energy. Here's my sigma 1s. And then slightly higher in energy is my sigma star 1s. Okay. Bearing in mind that this is all based on the idea that higher up is higher in energy. Okay, and I'll have these little sort of guidelines. Okay, now what I'm going to do is I'm going to take my electrons from each side, so I've got 2 total, right, 1 from each atom, and I'm going to fill from the bottom. All right, and I have to follow Hund's rule in my filling. And this will make more sense when we do larger things. Okay, but since H2 is so simple, it's hard not to follow Hund's rule, right? But what I'm not going to do, so violating Hund's rule would be to take 1 electron and put it here, and the other electron to put it there. Okay, can't do that, right? Hund's rule says that I have to fill singly and then double before I move to a higher energy level. Okay, so following Hund's rule, I'm going to take and put my second electron there. Okay, so I have to fill a particular level before I can start putting electrons in the next level. Okay, but on the same level, I'm going to fill them singly before I pair them. All right, and like I said, that will make more sense when we do more complicated molecules. All right, so let's take a look at bond order. Right, we talked about bond order once before, but we have a slightly new way to look at it. So bond order, when we're dealing with molecular orbitals, is 1/2 the bonding electrons minus the antibonding electrons. Okay, so in our case, sigma 1s, those are the bonding electrons, right? And the star are the antibonding. Okay, so my bond order for this molecule, 1/2, I have 2 electrons in the bonding minus none in the antibonding, means that I've got a bond order of 1. And if you remember, a bond order of 1 means that I have a single bond. Right? And that's what we would predict. That's what we've, seen before. That when we draw molecules of hydrogen, dihydrogen, they look like this, right? And so we would expect there to be a single bond. So let's see what happens. Let's play around a little bit. And that's kind of the fun aspect of molecular orbital diagrams, is we can try things that really shouldn't exist and we can show why. So let's take a look at what would the MO diagram be for H2 2 plus, right? So that means that each hydrogen atom should have 2 electrons, or excuse me, 2 minus. What am I saying? H2 2 minus. Okay, so I'm gonna start with, on one side I'll have hydrogen A and the 1s, hydrogen B on the other side, it's 1s. Okay. And in the middle, I'm gonna have slightly lower in energy, my sigma 1s and my sigma star 1s. Now each of these, since it's H2 2 minus, each one of the hydrogens should have 2 electrons. Okay, so I'm going to take, I've got 4 total to play with, 4 total to put in my central part of my drawing. So I'm going to fill from the bottom first. Fill from the bottom. So I've got 1, 2, 3, 4. Okay, so I take my total from the outsides, total number of electrons, and I put them in the center of my drawing. So let's look at the bond order. 1/2 the bonding minus the antibonding. So I've got 2 electrons in the bonding, and in this drawing I've got 2 electrons in my antibonding, which means a bond order of 0. Right? Bond order of 0 means that this shouldn't exist. Cool, huh? So we can demonstrate, right, based on this bonding theory.